Hello, my name is Owen Whitaker, and this is my report for Lab 2, Charge Tape Revisited. The purpose of this lab was to create a computational model that treated the two tapes as lines of charge rather than two-point charges and compare the necessary charge on each tape, or Q, from both models. Before beginning this lab, we must understand the fundamental physics principle that charge distributions can be modeled through integration, or in more simpler terms, the sum of infinitesimal point charges. In this lab, however, we will use a finite number of charges with finite masses and charges. We will also use Newton's second law that the net force equals ma. Because acceleration equals 0, the net force also equals 0, and thus the magnitudes of the electric and gravitational forces must be equal. From this lab, we found that the required charge in a line of charges was greater than with two-point charges. Through this report, the reasons behind this will be explained. For this lab, we used the same charge tape experiment from Lab 1. In this, two pieces of U-tapes with about equal charges were created by pulling them apart from another piece of tape. One of these was draped between two supports, and the other was held at a distance below and moved closer until the upper tape began floating. Once it began to float, the distance and the tape length were measured, allowing us to calculate the mass. In our model, the system was the upper tape and the surroundings were the lower tape and Earth. The initial conditions were the distance of 0.025 meters and the charge of 1.31 times 10 to the negative 8 coulombs. This was found by isolating Q in Coulomb's law and assuming the two charges were equal. This assumes we have two-point charges, however, which is why this value gets altered later when we treat it as a line of charges. Each sphere represents a small piece of charge on the tape. Every green arrow is the sum of the electrical forces on one upper segment of charge from all the lower pieces of charge. The white arrow is the electric force on the upper tape, and the yellow arrow is the gravitational force. We began our code by defining our constants, 1 over 4 pi epsilon naught and g, as well as assigning our variables of mass and distance. Then, we initially calculated Q using Coulomb's law and two-point charges. However, this value was unsuccessful in making the net force equal 0, which is why we altered the value of Q and the printed code later on to do so, as seen on the left. We then defined the electric field function we've been using for the past few labs, which will be used heavily later on. From lines 32 to 48, we created a line charge function. In this, each sphere has a mass and charge equal to that total value divided by the number of point charges used in this approximation. We then model the top tape and bottom tape as line charges using the function we just created. In this, n is the number of point charges in the line. We use 10, however, the more you use, the more accurate Q value you will get. We then created some scale variables which will be used to scale the arrows later in the code. We then create an arrow for every segment of charge in the upper tape. To do so, we used the electric field function we previously defined. With this, we found the sum of the electric field at a specific upper tape segment from each charge segment in the bottom tape and iterate through every top DQ. With these electric field values, we multiplied by the charge at these upper charge segments to get the electric force at each segment. We then create arrows for the net electric field and gravitational forces on the upper tape. To finish our code, we print all of these values out. Because our initial Q value did not produce the proper output, I altered the Q value until the magnitudes of the electric and gravitational forces were equal. From this, I got a required Q that was 2.89 times 10 to the negative 8 coulombs. This was greater than our Q value from Lab 1, which treated it as a two-point charges by a factor of 2.2, which is a very substantial difference. This is because, on average, the point charges are farther away from each other. However, I will discuss this more on the next slide. The assumptions we made in this lab were that the tape was not being kept up by any air draft and that the normal force from the support beams also were not causing any upward force to the tape once it began to float. We also assumed that each tape had the same amount of charge evenly distributed across the tapes. If we modeled each of the point charges as a singular charge rather than the line of charge, the necessary Q value would be much less. As stated before, the required Q of the line charges was greater than the required Q for two-point charges by a factor of 2.2. This is because when there are two-point charges, this implies that all of the charge is at the closest distance possible from each other. In reality, however, this charge is spread out amongst the entire tape, and the charge on one end of the tape is farther from the charge on the other end of the other tape. Because the charges are on average farther away from each other, this causes a lesser net field and electrical force. Thus, the overall charge of the tapes must be greater in order for the net force to equal 0. To conclude, charge distributions can be approximated as the sum of infinitesimal point charges. In this experiment, we successfully constructed a more accurate computational model by treating the pieces of tape as a line of infinitesimal charges rather than two-point charges. From this, we saw that our value of Q had to be greater. This is a result of the charges being at a greater distance from each other than with 2-point charges, and as Coulomb's law states, the greater the distance apart, the greater the charge must be to create an equal force. As the number of charge segments increases, the value of required Q becomes more accurate. For example, we use 10 charges per tape, but if we used 100, the value would be closer to the theoretical one. As this number approaches infinity, the value of Q approaches a limit, which is the theoretical real value of the charges. Thank you.